Why do astronomers use X-rays to observe the universe? And how do you build an X-ray telescope? This episode, we're speaking to Dr. Charlie Feldman from the University of Leicester about X-ray optics, China's Einstein probe, and what X-rays could teach us about the solar system.
Hello, I'm Charlie Feldman, and I'm a postdoctoral fellow at the University of Leicester, and I study X-ray optics.
Thanks very much for coming on the podcast today. It's great to have you on. Yeah, so throughout the podcast, we're going to be talking about X-ray astronomy and in particular the Einstein probe, but I did think it was worth just kicking it off with that sort of simple question. Why do we observe the universe in X-rays?
There are many benefits to observing the universe in X-rays. X-rays are usually emitted by the hottest and fastest particles and mechanisms in the universe. So it enables us to study things like gamma ray bursts, the event horizons of black holes, and even, in the case of one of the missions that we're working on, the aurora around the Earth, because the solar wind interacting with the magnetosphere actually produces X-rays, and we're able to image those with our optics. So X-rays are very, very useful. And because they are usually from the hottest part, when something like a gamma ray burst goes off, for example, although they're called gamma ray bursts, they actually give out X-rays first. So if you can capture that information right from the very beginning, then you learn a lot more about the mechanisms that are producing those X-rays.
Yeah, that's one of the things I was reading about. It was that X-rays are used for capturing those. What astronomers always refer to as transient phenomena, things that just happen and then they end really quickly. I mean, so it must be a really, really sort of exciting branch of astronomy to be in.
Yeah, it's not actually the area that I'm in because I only do the optics, but a lot of the missions I work on are looking for transients, and it is trying to capture them within seconds of them going off, because you might miss all the vital information if you don't get there fast enough. And that's the benefit of wide field of view X-ray telescopes like the Einstein probe and some of the other missions that we've worked on, is that because the field of view is so large, it doesn't matter where in the sky it goes off, we're able to capture it as soon as it does. And that's the goal, really, is to see as much of the sky so that as soon as something goes off, you are able to start recording information, getting those X-rays, getting the images, knowing where it goes off as well. So you're localizing where in the sky that's going off and being able to then steer other telescopes at other wavelengths towards it so that you can get as much data as possible as soon as possible.
Awesome. Do astronomers use X-ray for things that aren't transient? Do they use it for studying things like galaxies and nebulae? And do they even use it for like solar system objects?
Yes, I'm currently working on some projects looking at the X-rays coming from Jupiter, for example, because Jupiter is in such a large radiation field of its own, and because it spins so quickly, there are actually high excited particles going round Jupiter, and actually it's the most powerful synchrotron in our part of the solar system. So by studying the X-rays, you're able to understand the mechanisms of, Jupiter's magnetosphere, and because it doesn't interact with the sun because it's so much further away, unlike the Earth, we don't really know all the mechanisms that are going on, and it would enable us to be able to study that. But you're also able to look at things like supernova remnants, for example, that give off X-rays. Black holes give off X-rays. There are other highly charged objects within the galaxy that give off X-rays. For instance, Cassiopeia A, the Crab Nebula, these things give off X-rays, and so you're able to image them at multiple wavelengths, and that gives you additional information then to be able to work out exactly what's going on there.
Yeah, that sort of idea of multiple wavelengths is really key, isn't it? Because I suppose it's sort of, early astronomers just had their eyes, didn't they? But now we can observe the universe and we can see things that we can't see with our eyes. Isn't that right?
That's exactly right. Radio waves, for example, play an important part as well, because for things like gamma ray bursts and transients, quite often, very late on, when you can no longer see it in the X-rays, you will see a signal coming in through radio waves. And that gives you extra information as well, because it will normally end by going towards the lower parts of the electromagnetic spectrum. We still can't see those, but they are an important part of what's going on within the star or the galaxy or whatever that's giving off these radio waves.
It's absolutely fascinating. I mean, it's probably worth moving on to the Einstein probe, because it's a Chinese mission, but I understand you and your University of Leicester colleagues have been quite heavily involved in it.
Yes, it's a Chinese mission, and it's their first X-ray telescope, but the European Space Agency had a big role to play in it. And because the European Space Agency was involved, they asked for assistance from specialists across Europe with certain aspects of the mission. For instance, the Meteolario in Italy built the traditional Volta telescope that's in the middle of the whole satellite. Then at MPE in Germany, they were developing the detectors for the follow-up X-ray telescope, which is in the centre. And then we were the University of Leicester was responsible for helping with the wide field X-ray telescope, the WXT, which was a series of lobster eye telescopes, 12 modules in total. And we were asked by the Chinese to help them because we have the expertise of working with these optics, whereas they've never done it before. So they were asking for help with testing plans, actually doing some of the tests and helping them with analysis and interpreting what the data was actually saying so that they could calibrate the instrument. We also led the calibration of one of the flight modules that was done at Panther, which is in Germany as well, so that we could get all the data and then they could cross-calibrate with the data they had in China to make sure that what they were getting from the instrument and what they were getting from their own facilities, which were brand new and built specifically for this telescope, could be calibrated and they knew exactly what they were getting out of it. So we've been working with the Chinese since, I think originally the first talks were in about 2013, but we've been properly working on the mission since 2019. So it's been quite a long time, really.
Yeah, indeed. You mentioned the lobster eye optics, and that was something I really wanted to ask you about because it's so interesting. I guess that sort of cropped up a few times when I was reading about the mission and University of Leicester's work in it. Just explain why lobster eyes.
It's actually most crustaceans' eyes, really, rather than just lobsters. But basically, lobster eyes work by having this large field of view and lots of pores of very narrow pores pointing across a sphere. And the reason that they have eyes like that is that they generally live in very low-level light conditions and need to obtain as many photons as possible to be able to create an image. So they have this sphere eyeball, and then below it they have a sphere retina. And then all the pores across the sphere of the eyeball are pointing to this spherical retina to create this image of what they're seeing. And by having all of these pores, and they're so narrow, they're able to collect loads and loads and loads of photons. They also have this really large field of view, which is great because then they're able to see prey coming from loads and loads of directions. And in 1978, there was a paper that was produced by somebody in America who suggested that we might be able to produce X-ray optics, large field of view X-ray optics, by copying lobsters' eyes. So we have glass optics, which are made up of these really, really tiny pores, micropores. So they're called micropore optics, generally about 40 microns in width. and they're square, and we have this huge array of them, millions and millions and millions of these pores, so we're able to collect loads and loads of photons. They're then slumped to a spherical shape, and each optic is actually only about 4 centimetres by 4 centimetres, so they're really not very big, but then we tessellate a large number of those over a larger sphere, and we're able to create a full large field of view optic. In the case of Einstein Probe, the optic has 6 of these MPOs by 6, so you have a total of 36 MPOs, and you're actually able to image half the sky in one shot because there's such a large field of view. Now, they do have 12 modules, so there's an awful lot of these modules, but each individual one has a huge field of view, which will enable the satellite to see any transient or gamma ray burst or, exploding star as soon as it goes off, because they're seeing so much of the sky in one go that it doesn't matter where it goes off, they'll probably be able to see it. So yes, it's based on the principle of lobster's eyes. We don't actually use any lobsters to make our optics. And I have had several questions about the care of the lobsters when producing these optics. So yeah, we don't actually interact with any crustaceans.
Yeah, so it's like no lobsters were harmed in the making of this.
No lobsters were harmed, no.
Yeah, so that's obviously because X-ray is used to study these transient phenomena, so you need a large field of view. Is that also why it was launched into space? Because a ground-based telescope wouldn't have that field of view?
It's not just the field of view, but also the atmosphere absorbs X-rays pretty early on, which is a good thing because we'd be irradiated if the atmosphere didn't protect us from the space X-rays. Through the atmosphere, the really, really high X-rays can probably travel just over a metre. So if you think about the X-rays that you have when you've broken a bone or something, those are high energy X-rays. They can travel a short distance in the atmosphere. But when you're trying to get from space all the way down to the surface, the X-rays have already been absorbed by the atmosphere. So you can't do X-ray science from the Earth. You have to go into space. So all X-ray telescopes are always launched into space.
Oh, okay. I think I was reading also that those lobster optics were also used on the Bepi Colombo mission too. To
yes,
Mercury?
we were involved. From the University of Leicester produced an optic, a whole instrument called MIX, which is the Mercury Imaging X-ray Spectrometer, which is on Bepi Colombo. And actually, I built a small part of that optic, so I can actually say that I've built something that's in space, which is cool. But yes, we used the principles of these lobster eye optics, and in fact that was the first lobster eye optic to be launched into space, but because of the way they're getting to Mercury, it's not going to be operational till 2026, so we've still got a while to wait. And the lifetime of the Einstein Probe mission, I think, is 2 years preliminary, so Einstein Probe technically will finish before Bepi's even got to Mercury. So, we've worked on quite a few missions in between, but MIX was our first instrument that we built using these optics. But that's where our expertise comes from and why the Chinese asked us to help them with their mission.
Yeah, I'd be really interested to know a bit more about that, sort of specifically your role in this and other missions. What do you sort of do on a day-to-day basis when you're working on a mission like this?
I am responsible for optic design, modelling and testing. So I do an awful lot of sitting at a desk and doing computations, trying to work out the best combination of optic thickness, size, to get the field of view that we require to be able to do the science goals of each mission. So I would design the layout of the optics. Now, I didn't do that for Einstein Probe, but I have done it for a mission called SFOM, which is a French-Chinese mission, and is also going to be looking for gamma ray bursts and transients, and is due for launch in June of this year. But I was responsible for the design of the optic, the design of the electron diverter, which sits behind the optic to stop electrons flooding the CCD and destroying the images. And then I've also been responsible for writing test plans and going to the test facilities and to test the optics and make sure that they're working as we expect. and then producing models to show that they are performing as we would want them to in order to achieve the science goals. So I do all of the work from the very beginning of the conception of what the optic might look like, all the way through to the full testing of the final flight model. And it doesn't matter which mission it is, that is my role. So that's what I've done for SVOM, and for BEPI I had a slightly different role where I was doing a lot more of just the testing and I was doing some of the building. But then for SMILE, which is a European Space Agency mission, which is going into low Earth orbit to look at the solar interaction with the magnetosphere and the charge exchange between the solar wind and the magnetosphere. So that's an Earth observation instrument, but it's using a very similar optic. So I was still involved in the design of that and working on the testing and everything. So yeah, it's a lot of fun.
I'm sure it is. I'm sure it's absolutely fascinating. And is the physics behind this sort of optics pretty much nailed down, or do you take things from previous missions and go, well, that worked well, that didn't work well, and then you sort of it's sort of adapted along the way?
Yeah, the X-ray optics themselves work in the same way, no matter if they're a traditional optic like a Volta, where they basically look like nested dustbins. But those are huge and they weigh a lot. The science that the X-ray reflection that they use is exactly the same to ours, but our optics weigh an awful lot less. The problem with our optics is that because you've got all these millions of pores, you want each of them to focus at exactly the same point, and getting a square glass plate to slump and be a sphere and all of those pores to be pointing in exactly the same place is really difficult to do. And so whilst we do learn from previous missions, we are always trying to improve the optics so that we can get a better and better sensitivity, be able to improve the resolution. So if you think about the first cameras on phones, for example, and how much clearer and cleaner and crisper the image is now, that's effectively what we're trying to do. We're trying to make these images as good as we can so that we are able to get as much science out as possible from whatever the mission goal is, whether it's looking at another planet or looking at exploding stars or looking at the Earth. It doesn't matter. We're trying to just improve the optics.
And with the Einstein mission in particular, do you have sort of particular hopes for it, for what it might achieve?
Well, it's already achieved a huge amount because it's just so big, but just that it proves how good lobster eye optics are, because they're so light, you can get such a good field of view, and just proving that they are a fantastic way of creating an X-ray telescope so that we can get on future missions and go to new places like the outer planets, for example.
Yeah, that was sort of going to be my final question. You know, if ultimately, if funding were no objective, were no limitation, can you sort of conceive of like a dream mission, like as a sort of dream scenario that you would
personally, love? I've recently started working, as I said at the beginning, on the idea of going to Jupiter and looking at X-rays at Jupiter. Now, there's several aspects to that, and I've actually got a PhD student who's looking into this. But you can either look at the Jupiter system as a whole and how the planet creates its magnetosphere and the charge exchange mechanisms you've got there, but also how the moons interact as they're going in and out of the radiation belts, because each moon is in a different part of its magnetosphere and in the radiation belt. So you can look at all those interactions, which would be fascinating. But you can also do the mixed science, so looking at the composition of the moons using X-rays, because whereas for mix, you've got the sun illuminating the Mercurian surface to give you specific X-rays depending on the chemical composition. For the moons at Jupiter, you've got Jupiter itself producing these X-rays, and illuminating the moons and giving off X-rays. So we'd be able to find out what each of the moons was actually made up of, rather than just guessing. And whilst we have got X-ray missions which are in Earth orbit that have been taking X-rays of Jupiter, we've got a few photons. Because of the distance, we really don't have very much information, and also because there's such narrow field of view and we're so far from Jupiter. Jupiter's just a pinprick. So being able to actually go to Jupiter or Saturn and do the same thing, because it's got lots of moons, looking at how everything interacts. And some of the moons have magnetospheres themselves, so you'd be able to study that as well. So there's so many things that you could study. For me, it's getting an X-ray mission to the outer planets.
Awesome. That would be amazing. Is that something that presumably there are opportunities when planetary missions are launched for scientists like yourself to sort of say that this is what we should have on board, we should have this on board?
Yeah, the trouble with Jupiter is that we've got several missions that are heading there already, and it's trying to convince the space agencies that they need another one.
Yeah.
But we do also have the advantage that Lobster Eye Instruments is so light that we have a good chance of getting onto some of these planetary missions, and that's what we're trying to do. But yeah, trying to convince people that this is the best science is what we're always trying to do.
Amazing. Well, thanks for coming on the podcast today, Charlie, and sharing this with us. And good luck with the Einstein probe and Bepi Colombo and all your endeavours. And I hope you do get the X-ray mission to Jupiter.
Thank you.